Hello. Hello and welcome to this video. In this video, we will continue where we left off, that is from circular permutation. So grab your pen and paper as we start our read through for the theory of permutations and combinations. So circular permutation is about distributing objects in a circle. So consider that there are four objects A, B, C, D, and we want to arrange them in a circular fashion. Then we either take clockwise or counterclockwise direction we can choose. So in this case, counterclockwise rotation is chosen, and we have four such permutations or arrangements. Okay. So if there are n objects, then for each circular arrangement, there are n linear arrangements. This is a typing mistake. Should be a single n. But if n different objects are there, total number of linear arrangements are n factorial. So total number of circular arrangements are n factorial by n. Okay. So the value is n minus 1 factorial. So yeah, for each circular arrangement, there are n linear arrangements. All right. Thus, we can say that the circular R permutation of n elements is given by npr by r. That is n factorial by r into n minus r factorial. When the clockwise and anti-clockwise arrangements are same, then total number of permutations will become half of what we computed in previous case. That is npr by 2r. That is what it will become. Now we consider combination of sets. So we consider a set having n elements. A combination of a set S has a meaning of an odd-order selection of elements of S. The result of each selection is a subset A of the elements of S. So A is a subset of S. Thus the term combination and subset are interchangeable. Now let R be a non-negative integer. By an R combination of a set S of n elements, we understand an unordered selection of R of the n objects of S. The result will be an R subset of S. So if S is A, B, C, D, then we have four subsets of three elements. So this is called 3 subset of S. We denote the number R subsets or R combinations of an n element set by, it is the choose symbol, or you can alternatively write NCR. Choose means choosing R out of n, NCR like this, or like this, or like this. So obviously when we choose R from n where R is greater than n, then it will be 0. Also, if you choose R from 0, then it will be 0 if R is greater than 0. So we can deduce from this is that 0 from 0 or 0 from n or n from n or 1 from n. So these three will be equal to 1 and this will be equal to n. For 0 less than equal to r less than equal to n, npr is equal to r factorial ncr. So ncr is equal to n factorial by r factorial into n minus r factorial. It is read as factorial as we discussed in previous video. Let S be an n element set. Each R permutation of S arises from following tasks. Choose R elements from S. Arrange the chosen, which should be chosen, R elements in some order. The number of ways to carry out first task by definition is NCR. The number of ways to carry out the second task is NPR is equal to R factorial. By the multiplication principle, we have NPR is equal to R factorial into NCR. Now applying the formula of permutations, we have NCR is equal to n factorial by R factorial n minus R factorial. So that's how we deduce this value. So if you read from here, you should be able to understand the combination of R objects out of N objects. Then we have permutation of multisets. Let multisets have been discussed in previous videos. So if you don't know what is a multiset, I would request you to visit the previous video and watch it. Let S be a multiset with objects of k different types where each object can be repeated infinitely. Then the number of R permutations of S is k to the power R. To prove this, we can choose the first item to be an object of any one of the k types. Since the number of repetitions are infinite, the second item can also be chosen in k ways. In fact, any item can be chosen in k ways due to infinite repetition. Following multiplication principle, total number of such permutations is k to the power r. Let S be a multiset with objects of k different types with finite repetition numbers n1, n2 through nk respectively. Let the size of S be n is equal to n1 plus n2 through nk. Then the number of permutations of S equals n factorial by n1, this should be 1, n1, n2 and nk, n2 factorial and so on up to nk factorial. We can calculate this by thinking in terms of n places, and we want to put exactly one of the objects of S in each of the places. We have n1 objects of one type in S, so we must choose the subset of n1 places from the set of n places. We can do this in nc n1 ways. After this, we have n minus n1 places left, and we have n2 objects of second type. So following similarly, we can do this in n minus n1 c n2 ways. Following this way, invoking multiplication principle, the number of permutations of S equals ncn1 into n minus n1 c n2 into, we go on decreasing the n and we go on changing the r by the decrement. So if you see this n minus n1 factorial will get cancelled, n minus n1 minus n2 factorial will get cancelled, and so on. And at the end, we will have nk factorial from here, and n1 factorial from here, n2 from here, and 3 from here. So the final value is n factorial by n1 factorial, n2 factorial, and nk factorial through nk factorial. Let n be a positive integer and let n1, n2 through nk be positive integers with n is equal to n1 plus n2 through nk. The number of ways to partition a set of n objects into k labeled boxes in which box 1 contains n1 objects, box 2 contains n2 objects, box k contains nk objects equals the same value or same formula, that is n factorial by n1 factorial, n2 factorial is equal to nk factorial. If the boxes are not labeled and n1 is equal to n2 through nk, then the number of partition equals n factorial by k factorial into n1 factorial into n2 factorial multiplied with nk factorial. We can calculate this by direct application of the multiplication principle. So we first choose n1 objects from the first box, then n2 from the remaining n minus n1 objects for the second box, and so on. So we have this, which will lead to the same result. This, if the boxes are not labeled, then n1 is equal to n2 is equal to n3 through nk. Then the result has to be divided by k factorial, because each way of distributing the objects into k unlabeled, again a typing mistake, boxes, there are k factorial ways in which we can attach the labels to the boxes. Thus, using the division principle, we arrive at the result as n factorial by n1 factorial into n2 factorial through nk factorial. So there should be a k factorial here, which is missing. So there are quite a few mistakes. K1 factorial is missing here, which is a spelling mistake, and so on. Now we look at combination of multisets. In fact, let me quickly write down the mistakes so that I can fix those after recording the video. So one is k factorial is missing, k factorial, and we have nn. And what other mistake was there? Okay, I'll find it after the video. I don't need to worry about it. Now we look at combination of multisets. If S is a multiset, then an R combination of S in an ordered selection of R of the objects of S. Thus, an R combination of S is itself a multiset, a submultiset of R of S of size R, or for short, an R submultiset. If S has n objects, then there is only one n combination of S, namely S itself. If S contains objects of k different types, then there are k factorial, this should be k factorial, another typing mistake, combinations of S. Let S be a multiset with objects of k types, each with an infinite repetition, then the number of R combinations of S equals R plus k minus 1 CR is equal to R plus k minus 1 CK minus 1. Let k types of objects of S be A1, A2 through AK so that S is equal to infinity into A1, comma infinity into A2 through infinity into AK. Any R combination of S is of the form x1 into A1 in comma x2 into A2 through xk into AK, where x1, x2 through AK, xk are non-negative integers with x1 plus x2 through xk is equal to R. The converse is also true. Thus, the number of R combinations of S equals the number of solutions of the equation x1 plus x2 through xk is equal to R. We will show that the number of solutions of this equation is given by number of permutations of the multiset T is equal to R dot 1 into k minus 1 dot star of R plus k minus 1 objects of two different types. Given a permutation of T, the k minus 1 stars divide the R1s into k groups. Let there be x1s, there is again a typing mistake here, two ones have come. To the left of the first, x2 ones, okay, the ones are there, okay, of the two types. So R ones into k group, x1 ones to the left of the first and x2 ones between the first and second, and xk ones to the right of last star. Clearly x1 plus x2 plus through xk is equal to R. The converse of this is also true. Thus, required combination is given by the formula R plus k minus 1 CR is equal to R plus 1 minus 1 CK minus 1. Now, these are some formulas which have been derived already. So, I will not prove it. I would suggest you to pause the video, write these down, and then try to verify as many as you can. Some formulas have come from binomial theorem like number 9, number 10, and 11. These have come from the binomial theorem. We will study these when we reach binomial theorem. So explaining these is kind of not going to work at this moment. What I want you to do is you try to prove up to 8 and then prove number 12. So that is something I would like you to do. If you have problems solving any of these, let me know in the comment and I will give you an explanation. Then there are other useful results which we can read through. So number of selection of R objects out of n different objects when p particular objects are always included is PCP and into n minus PCR minus P. That is equal to n minus PCR minus P. When p particular objects are excluded, that becomes n minus PCR. Number of selections of R objects out of n different objects such that p particular objects are not together in any selection is NCR is equal to n minus PCR minus P. Number of selection of R conjugative objects out of n objects in a row is n minus R plus 1. Number of selection of R conjugative objects out of n objects along a circle is equal to n when R less than n, comma 1 when R is equal to 1. Number of selection of 0 or more objects out of n different objects is equal to NC0 plus NC1 plus NC2 through NCn is equal to 2 to the power n. Number of selections of one or more objects out of n different objects is NC1 plus NC2 through NCn is equal to 2 to the power n minus 1. So these two have come from binomial theorem. it will be difficult for you to prove 6 and 7. So for now, just try to make a note of the formula that this is the formula and we can use it. Number of selections of 0 or more objects out of n identical objects is n plus 1. Number of selections of 1 or more objects out of n identical objects is equal to n. So you can pause the screen and go through these. You should try to understand. So I will show the screen. You can pause the video and take a note of that. Now we come to permutations with the repetitions. The objective is to find permutation of R objects out of n objects of which P are of one type, Q of second type, and so on. Let the different objects be denoted by ABC. Consider the product 1 plus ax by 1 factorial plus a square x square by factorial 2 and so on through AP, a to the power p, x to the power p by p factorial into 1 plus bx by 1 factorial plus b square x square by 2 factorial through b to the power q, x to the power q, q factorial. So required number of permutations is sum of all possible terms of the form r factorial by p factorial q factorial through and so on into a to the power p, b to the power q, where p plus q and so on will be equal to r, which is essentially r factorial into coefficient of x to the power n, x to the power r in this product. Okay. So basically what we have done, we substituted a is equal to 1, b is equal to 1 here to get this formula, and we are trying to find the coefficient of xr in that. Now we consider combination with repetition. Let me see how much is it. It's a big one. So it is best to start on this with a fresh mind. So in the next video, we will resume here. And once again, I will request you to go through these 14 results, pause the video and try to prove these. Take it as homework. And I will end this video here. I hope that you are enjoying this playlist, and the theory is definitely boring. Okay, there is no denying. I also don't like theory, but we have to go through theory so that we can solve the problems. Because when I will start solving problems, I'm not going to explain the theory part of it. That is why I'm taking it slow and making small videos. I don't want to burden you with a lot of theory right away. So we will meet tomorrow again, and I will do combinations with repetition. So not much is remaining. There are certain formulas. We have integral solution of equation, general applications. So these are mostly exemplification. Then we have inclusion, exclusion principle, and derangements, ejection principle, occupancy problem. So these are not big ones. So with this, I'll end the video here. Thanks a lot for watching my videos. It means a lot to me. And I'll try to give my best for your education. And I hope that you succeed in your life. And I wish you very best for exams and study. So once again, thanks a lot for watching the video. We will meet tomorrow in the next video. Thank you very much.